to record. And this is also going to get transcribed. So the video is going to be available to you on HCAN anytime you actually log in. Whether it's going to be uploaded to YouTube or not, that is a question for your presidents of HCAN. So if you want this video on YouTube for your future reference, because this is my last semester teaching, please actually request them to upload it if in case you do want the videos. So your exam 2, I do have your exam 2 questions, and it will be a very regular exam, like, the same as exam 1. So nothing special. I am, however, going to stress on topics which are going to be important for obviously exam 2. I hope you actually did well in your re-exam today. And of course, I also hope that we don't have to actually repeat this exam again and again, So we want to actually learn all the concepts and more importantly, what is important for the exam. Now, again, I'm more than open to discussing concepts and questions, especially this is a mathematics based course. So some of you might not be familiar with signal processing or deep signal processing techniques that are actually getting used. If you are not, do this mechanically and then come and talk to me, understand the questions, and then we can take it off from there. But if you do understand it, then these are the questions that are going to be important for you. So these are the same slides that actually we worked on last Thursday. And these questions are going to be important, not exactly in this format. Maybe the question functions are going to be different. But yes, you do have to find out a variable, and then you have to probably plot it, and then probably find out a couple of, values for probabilities. And then, of course, very important is your mean and variance. Your test right now, as I can see, it has 3 questions. And the questions are okay, I would say. If you see something that is unfamiliar on the paper, try to take it as it is, okay? By which I mean that if you have not learned that concept, probably in sometime in the future, try to solve the problem as is. And I'll tell you what I mean by that in a minute. But mean and variance, I see mean and variance covered in one question at least. So yes, mean and variance is important. And CDF, of course, CDF, PDF is of course important because I mean, duh. And let's see. Yeah, finding PDF or finding CDF and staying within the range and characteristic function is important. So we are going to go over those. So this particular type of problem, again, if you are not familiar with the steps, please become familiar because the function might be different. Again, the process is the same. Function, sometimes you all do have advanced calculators to actually process the values. But out here, again, we have used the simple property of PDF. Again, if you go down, if you're making your cheat sheets, please go down to your probability density functions. And these are the properties of the probability density function. So property 1, 2, 3. And the fourth property that you see, that's exactly what we are trying to use out here. And that actually means that we are integrating the entire thing to 1. Please be aware of the limits of integration. Whatever is stated in the problem, that is going to be the limits of the integration of this problem. You solve for that values of C, and whatever the value is, substitute it, and then give your PDF as an equation. And then, of course, sometimes you are going to be told to find the CDF. Let me re-verify that. Yes, you do have to find the CDF in at least one of the problems. So yes, you find the CDF by just integrating the PDF. And the integration limits for this time is 0 to x, not 0 to 1, because this is going to be a function in x, because it goes up to a certain limit. Remember, the CDF is not a continuous range. It goes up to a value called x, and that is why the upper limit of this integration is x. And you solve it exactly in terms of x, and whatever comes out, you just write that down, right? And if you by any chance have to find the ranges, so you can do it in two ways. One is, of course, you can find out the integration by integration. Like you can put this in the PDF and then find out the integration of that. Or you can straightway use the CDF. That means fx of half minus fx of 0. So that's the straight way of doing it. It's less time consuming. And fx of x equals 1 is 0 only and only when if it's a continuous function. Now, if you can actually plot the CDF and the PDF, you'll soon find out that this is basically a continuous function. We don't have any discontinuities, and hence for one specific point, the value of that specific point might not be like we say it's half, but then when we are trying to find out the exact value of that point, it's impossible for us to find that. So we usually deal with ranges and not with the exact values unless it is a discrete random variable. We are not dealing with discrete random variables as of now. This is a continuous random variable, so the value is 0. Now, for the other half, so if you have like something like A minus B kind of a format where A and B both are positive values, or B can be, so they are not 0. Either of them are not 0. Then what you do is you basically just substitute the values of the range of B minus the range of A. This is also a part of the properties, but this time you have to go to the properties of the CDF. And the property of the CDF that we are trying to use is property number 6, which is basically fx of B minus fx of A given a range. Okay, so this is the property. So this guy is the property that I'm talking about. I'm just going to maximize it a little bit. So property number 6. So all the properties, that's how you use them. And then, of course, we go down to the function expected value and variance. Remember, expected value is just the PDF multiplied by X, but expected value and variance, these are numbers. Okay, so numbers needs to be calculated like numbers. All right. And what I mean by that is substitute the value ranges. Okay. Now, expected value of whatever is there inside the braces, they will follow the same format. Okay. So whatever is there inside the brace, that's going to be the X. Fx of X does not change. So if this is X squared, the X squared is going to change. Fx of X still remains the same. Okay. So this is just a value. Again, this is also a value. So variance is basically E of X squared that we just found out minus E of X whole squared, and just substitute it in your calculators and find the value. So this is a very straightforward problem, but in exam center, what happens is that we often forget the steps that we need to do in order to arrive at the correct answer for the ultimatum. So I hope you practice these types of problems. Now, this type of problem is not going to be there, so I'm not going to actually go through them today, but if I get time, I'll explain this problem later because some of you have asked me about this. Gaussian problems, I'm not going to say if it's there or not there, but I'm just going to lightly go over it. So for Gaussian, you know that you have to actually look up the tables. So what has come to my attention is that some of you are getting, so I have gone through your homeworks because I'm not graded them, but I have gone through your homeworks. Nevertheless, I always go through your homeworks. So some of you are getting confused with these two terms, which I'm going to clarify today. So when you talk about the important random variables and you go down to Gaussian, so the phi of x minus m over sigma, this is called the characteristic function. So anything to do with the phi is a characteristic function. It happens so that the characteristic function of the Gaussian looks like this. And what does it mean? It means, so if you expand phi of x minus m over sigma, you get 1 over root 2 integration of minus infinity to x minus m over sigma e raised to t squared by 2 dt. So this is what it means. Now, if you go to the transform methods, you will also find something called as characteristic function. So the characteristic function out here is a random variable, not Gaussian. Okay. So when you are being told explicitly to find out the characteristic function of a Gaussian random variable, or trying to find out in difference with trying to find out the characteristic function of just any function, right? So the characteristic function of just any function is basically so what is this expression though? So first of all, we have to learn that this is the expected value. Now E of x. So remember, I said whatever is there as in the format of x, that gets substituted out here, and the fx of x still remains the same. So that is your characteristic function, and this is what you need to solve in case you're asked in the exam. Okay. Now, of course, j is -1, so it's imaginary, and there goes the story of everything. But the point is that if you have to find out the characteristic function and there's nothing, no other statements mention that this is Gaussian or this is that, please use this formula. So I hope you have this formula written down on your formula sheet so that it can actually help you. Now, going back to the problem sets, the characteristic function that we have mentioned out here, yes, that's the same function, but it's in the Gaussian format. Okay, so the Gaussian format is x minus m over sigma. That's the Gaussian style of doing things. So again, same thing. If it's greater than 4, you have to convert it to less than 4. You can still process with greater than 4. I don't have any problems with that. Sometimes we directly do that. And it's nothing wrong in it. It's just that the negative portion makes much more sense, much more familiarity, because it's the CDF expression directly. So if it's greater than 4, you convert it to less than 4, and then you keep subtracting, but the characteristic function will not change. Out here, the mean is 5 and the standard deviation is 4. So you keep equating it and leave the negative sign is inside, then convert that negative sign into positive sign, and then look up this value and subtract it from 1. So similarly, all the other ranges, if you have a range of values, it's just the first 5 function of 7 minus the second 5 function of 2, and then whatever comes out, right? So Gaussian is kind of very straightforward. Now for these kind of problems, you might actually interface that there is a function. So if we say y equals fx, it's just a function, right? So let's go over this one though. So please forgive me, I'm writing with my pen. I mean, I'm writing with my mouse. This is not like a laptop or anything. Like I'm using my mouse basically. So if you have fx of x, okay, and I say y equals fx of x. Now, this is just a function, right? If I don't tell you that this is a PDF or whatever, you just treat it as a function. So that's exactly what is going on. So fx of x, so this is your same as high school math when you said y equals fx, right? And then you created a table of y, and then you created a table of f of x, and then you plotted it together. Remember that problem? If some of you have solved that. So it's the same thing, but for us, that equation has been, this has been kind of weighted and then bias added to it, right? So now you're trying to find out the mean and variance of y with respect to x. Now, well, x itself is unknown, right? So a couple of you guys have come and talked to me. Again, x itself is unknown, but you can definitely use the formula of the mean in itself because mean is an operator. And you're going to soon learn in chapter 5 that this is more than just an operator. It can slide between variables. So if you have 3x plus 2, and then you have to apply the expected value operator onto this entire 3x plus 2, what is going to happen is it's going to slide through the 3 because 3 is not concerned with an expected value. Expected value of 3 is 3. Expected value of x, however, we don't know what the expected value is, so we'll write that down. And expected value of 2. Well, what happens with that? So let's find out. So the expected value operator just slides over constants. It does not have anything to do with the constants. But what about the variance? What happened there? So variance, for example, is going to slide and is going to modify some of the the different types, I would say, you know. So the variance of 2 is 0, but the variance of but the expected value of 2 is basically just 1. So the variance is expected value, but a little bit more than that, right? So if you have gone through the formulas of variance, you would actually find out that variance is basically e raised to x squared, right? So you're doubling the value of x and then subtracting it from the mean. So this is almost like a weighted mean kind of. So it's exactly the variance that we have studied in our high school, right? Nothing different than that. So the expected value operator goes and sits on 2. Well, 2 expected value of 2 is 1. So, but the variance, for example, it goes, it slides over. So variance is like x squared terms, not x terms. So this is basically your terms in x, right? But this one deals with x squareds. So what happens is that variance of 3x plus 2 could be whatever the x presents in itself is, but for 2, it's non-existent. And variance of 3 can be actually separated out. Variance of 3, whenever you take the variance outside the bracket, make sure you square it, because the variance deals with x squared and not x. That's why it's 9 var of x. Okay. Now, had this been a Laplacian random variable, we would have this specific combination. Where did we get this from? Well, we got this from the table. What table is it? What table am I referring to? Well, it's this table that we all know so well. Oops. I think I left it before. So again, um, where is it? Am I scrolling too fast? Yes. So these are the different types of random variables that you have, right? So uniform, yes, uniform variable. Now somebody actually asked me, why is uniform variable a discrete and a continuous? Depends on what type of use you have. Okay. Exponential is of course a continuous random variable. Gaussian is a continuous random variable. So is gamma, and so is zip, so is Pareto, so is beta, and so on. So out of all the different types that you have out here, the type that, let's see, right? So we have Laplacian out here. So Laplacian, you know the PDF, you know the expected value, you know the variance. So for us, the expected value is not required. Why? Because we are not asked to find that, right? We are asked to evaluate the mean and the variance of y if x is a Laplacian. So if x is a Laplacian means that the expected value is basically 0 and the variance is 2 over 2 alpha squared. So whatever alpha is not given to us. Now, similarly, you can find the variance of it. So if the variance of x is so and so, what is the variance of y? Or what is the expected value of y? Okay. So again, if it's Gaussian, if it's so and so forth, right? Now, this one is important in terms of you to know how to tackle the problem when we do have a very prominent Fy of y. So, excuse me. So if you actually go over problem 4.12, let's actually go over it. So this is your CDF for that. So the PDF, actually in the fourth homework, you actually did find the PDF of this one. So with that PDF information in mind, what do we have out here? So with that PDF, if y is equals x, 2 of x plus 3, and x is a random variable in this problem, find the CDF and PDF of y. Now I'll tell you why this is significant. So this is not significant in perspective of your exam, but why are you solving these kinds of problems? Now remember, I gave you an example of ChatGPT on how it kind of generates new things from old things, right? So if you input, if your input is, say, for example, I don't know, a text document, and you label that as X, and you have like 5 paragraphs and you don't want to read it, and you want ChatGPT to summarize it. So your new output now is going to be a function in which you're probably going to take the summary, okay? And summary is just a couple of lines, right? So not much. It might actually fit in just one page. So several 16, 17 pages of document fitting in one page is actually a skill set, right? So how does it do it though? So there is a scale version or a biased version or both actually available for this new function y. What y will actually do is as you respond to it, no, this is not relevant or this is not helping me, it will try to modify its own weights, okay, and try to give you the best possible outcome. So that is exactly why we need to learn y equals 2x plus 3, or rather function of one random variable. So f of x, I think, is already given to you in the problem. What you need to find out basically is the random variable CDF and PDF of y. Okay, so now everything is all about y. So remember how we started it? Fy of y, we don't know anything, any information, but we know the definition. So they have skipped a step out here, which I'm going to do. So basically, Fy of y is equals here. Oops, that's not true. Here they have directly substituted it as 2x plus 3. So if you don't know anything, start with the definition. P of y, you can now either use greater than or you can use less than, but they have out here chosen greater than. So, sorry, I'm so sorry, less than. So less than actually makes your life a little bit more easier. So I would say if nothing is explicitly mentioned, please select lesser than. It will make your life much more easier. So P of y, when y is less than some value, whatever, right? So this guy tells them, okay, great. So y is less than some other output parameter, small y, whatever it is. I don't care about it. What we need to do is to find out the PDF and the CDF. So how do you go about doing that? You take the values, you substitute the values. Remember substitutions? So this is substitution method. Now, is there any other method of solving? Yes. Yes, there is other methods of solving the same problem, but we do not cover it in this syllabus. This is called the substitution method of solving your functions of one random variable, functions of two random variable. So ultimately, you have to isolate x. Why are we trying to isolate x? Because we want to actually get to a point where this is a value. So this is no different than just y dashed, right? So you can write this basically as fx of y dashed. Why? Because fx, this term dictates what type of f is it, right? So if fy of y is defined by if Fy, understand this actually, oops, that's not correct. And this is an important concept actually, other than all the concepts that you learn. Fy of y is basically defined as P of capital Y, which is the random variable, less than whatever is sitting inside the bracket. Okay. So whatever is sitting inside the bracket. So whatever is sitting inside the bracket. So we had actually y minus 3 by 2. Guess where that y is? Here. So now nothing, no more information is given, so we cannot proceed further from here. But what we can do is to find out the PDF, right? So how do you find out the PDF? We actually differentiate it, right? So by differentiating it, what do? We basically follow the product rule. So the product rule, okay? I'm not writing the entire thing. It's called the product rule. Product rule teaches you the exterior part should be first differentiated, then go to the interior part and then differentiate and multiply both of them. So the exterior part, well, you don't have much to do with it, right? You don't know what fx is. So we'll just write it f dashed of y minus 3 by 2, okay? And then let's move on to y minus 3 by 2. So we find a half there, okay? So how come fx dashed? So again, remember from the formula, let's go back. Let's go to the probability density function and look at the formula of the probability density function. Fx of x, that means small fx of x is equals d dx of capital Fx of x, right? So ddf of, so small fx of x is basically d dx of capital Fx of x, right? So now if I have to find out the value of this small code, okay, so that's fine, like it's half, great. But you still have this f dashed x. So f dashed x is nothing but your small ff. Okay. F dashed means like you can also write this as f dashed x. F dashed of x. You can easily write that. So that's exactly what is written out here. So then what we are substituting is we are substituting this guy, since according to the definition, by the fx functions. Okay, this is not correct, but anyway. So the fx right now is just differentiation. Okay, so the fx comes from differentiating this, and this half comes from differentiating this. Okay, this should be clear. Now, yes, it's within the same range. Now, you can also find the range. Okay, finding the range means that you start with, well, what defines the function? So what defines the function? If you put 1 out here, the entire function definition is just going to go away. Similarly, -1, the function definition is exactly going to go away. So this function might be something between 0 and 1. That's why we actually plot the function. When we're plotting the function, it should be between 0 and 1. So, okay, great. What if it's 0.999999999? So what is the value of y according to, right? So find the CDF and PDF, right? Nowhere in your entire thing has it been told, give us the ranges, but you give the ranges anyway. Why? Because this is a function. Function always comes with ranges. Cool. So now this is fx of x. That's great. But we do not we should not stop at fx of x, because our question is find the CDF and PDF of y, not x, right? So fx of x is the step 1. Step 2 is to find out or substitute that into fy of y. So fy of y kind of looks funny, right? So it's basically 3/8, and I'll tell you where the 3/8 comes. Basically, you know that it's whatever is there, you multiply it by half because you differentiated it. 1 minus y minus 3/2 whole square. So whatever x was there, right? Whatever x square was there inside, that got substituted by this. So let's actually go to the problem 80 and see whether we have solved all the parts or not. So another thing that is going to be challenging for you in this exam is solving all the parts completely. Only 3 questions, but then time also flies, you know. So that's exactly what the question is saying, nothing more, nothing less. It's just amplified and shifted, and we are supposed to find out the CDF and PDF, and then the problem basically ends. So same thing out here as well. If y is equal to some function of capital X, find the CDF and PDF and then plot. Sometimes plotting is not going to be given to you. Find the PDF when x is Gaussian variable, in this case y is log normal variable, and then some other conditions. So I've given you the solution to exactly the same problem that we did out here. If you can do these couple of steps, you can actually, let's see, walk away with at least 25 points. But you have to remember this. So that substitution comes in. After substitution, limit adjustments. After limit adjustments, you find out the fy of y, which is small fy of y, which is the PDF of y, right? And then define if x is Gaussian or not. If it's Gaussian, then what are the limits of the function, basically? Yeah. What the? Now, oops, I don't know that. Nope, never mind. No, this is where we actually kind of ended, and this is something new for us, right? Why is it new? Well, first of all, we haven't seen it. That's why it's new, right? Why are we actually trying to solve for the characteristic function? Now, first of all, what is characteristic function? And is it there important in the exam? Yes, it's important for your exam. Now, this one that I'm trying to solve, I'll upload the solutions hopefully by today. Please, guys, don't curse me if I do it by tomorrow morning. But that's why I'm trying to actually give you the important parts that you can actually revise. I am really going through a very hectic time right now. Um, so this was 102. Now I do have the reliability question. Honestly, I'm going to explain you the reliability concept, but it's not really that important for the exam. Let's put it that way. Okay. Anyway, so now we are going to do characteristic function, but then before that, but this question is actually a little bit more characteristic function, and then you have to find the mean, you have to find the variance, and then you have to actually find it not by your normal means. You have to actually basically apply the momentum theorem. So we're going to talk a little bit about that as well. So where are we? First of all, where do we locate them? You go to the transform methods, which is unit 4.7. And as soon as you open the transform methods in your book, you will actually find the characteristic function very, very prominently expressed. So transform methods are very, very useful, very useful. If you would have actually been in the original probability course that we are that gets taught by Dr. D, what we did actually there was a practical application of transform methods done via images, right? So we do transform methods all the time in image processing. Image looks like something, and then we turn it to grayscale. So I can actually show that to you. Um, so say, for example, this is an ideal case of transform where we have like a colored image and we transform that to a grayscale. So very, very common actually, not just in actually signal processing. You actually do transform methods in control systems as well. You do transform methods in, I think, everywhere you actually do use a transform method. Sometimes to actually fix stability and all those other things. You don't need to know too much of details of that, but it's nevertheless useful. So then, now since it's useful, we have to learn it. Okay, great. What do we do? First of all, take this down in the cheat sheet, right? Second of all, learn that this is an imaginary thing, right? Like J is imaginary, right? It's root of -1, right? Um, so basically, if you are a little bit into signal processing, right? A little bit, you don't have to be a whole lot. But by the way, guys, I'm going to tell you, I have been, and if you can talk to the presidents of both the presidents of the both the presidents IEEE and IEEE HKN. I kind of have been talking about this for a couple of years, actually, for now, that some of the students think that, well, I'm going to get into electrical engineering, like core electrical engineering. I'm going to deal with transformers and distribution networks. I'm seeking a job at Encore, or I'm seeking a job at, I don't know, anywhere that actually is like very hardcore, like it deals with power transformers or power engineering or stuff like that. So I don't need signal processing. Well, guess what? News flash. The basic thing that actually will be very, very important for you when you become an electrical engineer working for Encore, working for, I don't know, Lighthouse or something, is going to be communication and signals. You don't have to deal with the raw formats like these, but nevertheless, a study of communication really helped my students. They helped them in Lockheed Martin, they helped them in so if you are in RF, signal processing is the base. Even if you are in the power sector, signal processing is the base. Guess what? Photonics, signal processing is still the base. So you cannot escape signals. So please do that class. For those of you who are doing that class, please do that class very, very seriously and understand the functions. That's why Dr. Praja gives you functions which are a little bit more, unit step functions, Dirac delta function, or Kronecker delta function, unit steps, ramps. Then you can move on to sawtooth, and then you can go a whole lot better. But the point is that this is Fourier transform, guys. So if you are not familiar with Fourier transforms, that's absolutely fine. You don't have to know about this. But this is basically Fourier transform. So there are transform methods. Now let's talk about core electrical engineering, right? You have Z transform, you have Fourier transform, you have Fourier series, you have Z transforms, S transforms, so Laplace domain transforms, so S transforms. You have so many other transforms that I cannot even name. Now, why are these transforms important is because, you see, sometimes in a when a specific signal comes in, we don't know the characteristics of that signal, right? So we are trying to gather as much data as possible. And by doing so, sometimes it so happens that um, the frequency domain expressions are far more interesting and far more easier to understand than the actual time domain series. So as soon as you convert it to the frequency domain, it becomes so much more simpler to apply any of the um, different techniques. I mean, I'm not going to teach you Fourier series and transforms out here, but then you can apply various techniques. So that's why transforms are important. And you actually have done a couple of transforms without you knowing doing transforms. So transforms are not like new topic. Anyway, so what do we do though? So yes, that's a great lecture, but what do we do? So that's the basic formula. Okay, so this is a basic form. So do not rely on this form. First of all, check your limits. Okay, this is step one. Okay, and this is step two, right? Write down the formula. Now substitute the limits. Now be very careful of this E. Okay, this is not e raised to minus j omega x. Sometimes people are used to minus j omega x. No, this is e raised to j omega x. Okay, not the minus part. The minus ones are used in inverse transforms. This is j omega x. Okay, and then simply, substitute the fx. Now, how? Well, where is the fx of x first of all? In this function, where is the fx of x though? We need to find out. Now, sometimes it's given to you. You don't need to actually, try too hard to find it out. But if it's not there, this becomes your step two, and then this becomes your step three. Okay. So first of all, what is fx of x? So find the characteristic function of the uniform random variable. Now, it's easy for us to actually draw it, right? Like uniform random variable, very neat function, right? Here's my pen. Oh, there you are. So very neat function. Okay, yes, the PDF it looks like this, right? Great. You have minus b as one of the integrals, b as one of the other integrals. Great, right? But somehow the students are like, uh-oh, how do I write this function, right? Like, what does it look like? So if you actually, you don't need to struggle with that. In fact, we do already have a list of things that can actually help you. So look at the random variable. So the PDF is already given to you, 1 divided by b minus a, where a less than x less than b. So for us, the limits are minus b and b. So what does the fx of x now look like to you? This looks like 1 divided by b minus of minus b, right? And that is exactly what they have done out here. And then you multiply it by e raised to j of omega x, okay? And then dx. And then what about the range? The range is from minus b to b. Okay? And voila, there you have it. So you actually solve this integration If you have a calculator, great. If you don't have a calculator, please have the integration tables at the back of your cheat sheet, and you can very easily basically solve this entire thing. So that's part A. So find the characteristic function of a uniform random variable. Now, obviously, uniform random variable can be substituted by any other function. You have to follow the same method. You just have to basically take the Fourier transform of the function, and that's about it. Yeah. What about the mean and the variance? Now, first, if you have to find the mean and the variance, that's a great job. But then understand this point is important. Where's the pen? This Okay, yeah, this point is important. By applying the moment theorem. So you can basically, if I give you the function like fx of x, you can do this as well, right? Like, oh, okay, professor hasn't said anything. I am going to find e of x like this. I'm going to just take minus b to b, right? I'm going to multiply x, and then I'm going to take like whatever has come out here, that is e raised to j omega b minus e, oops, raised to minus j omega b whole divided by 2 j omega b. Okay, where did I get this horrible equation? Well, you solve this. This is where this is what is getting substituted out here. Why? Because the formula for the e of x, if you actually notice that, so the e of x is basically equals x fx of x, and that is from minus infinity to infinity dx. So that's exactly what I'm doing. I'm just taking that PDF, multiplying it with x, substituting by values, and we have a dx. Okay. So you can do this way as well. But no, what they have told us to do is to apply the moments theorem. Okay. So first of all, you need to know what is the moments theorem. So let's learn that. So moments are basically, you know how you tell ddx or d2 by dx2 or d3 by dx. So basically the differentiation power. Okay. So what do I mean by that is that if you differentiate once, you get a value, or an equation, whatever. If you differentiate it again, and then again, and then again, so those different powers are basically given by, or what is meant by the moment. Okay. So it kind of looks like this, dn divided by d omega n, but I'm trying to actually give you the exact moment theorem. So this is in your page, for those of you who want to take it down as a formula, this is in your page 185 of your book. You'll find it at the bottom of the page that the moment theorem states that the moments of x is given by x raised to n. If you find the expected value of that, that equals 1 divided by j raised to n, dn divided by d omega n, and then the characteristic function. So that is why, first of all, we need to first find the characteristic function and then use that characteristic function. Now, how do you know what is the moment? Like, do I use 1? Do I use 2 derivatives? Do I use 3 derivatives? Do I use 4 derivatives? How many times do I differentiate? So how many times do I differentiate this guy, right? So because the formula is d of n divided by d of omega n. So that many number of times we can basically just go on differentiating, right? Well, there is a point. The point is that first of all, omega should be 0. So whatever you do, omega should be 0. Now, if it's a simple thing like unit step function, the moment is 1. If it's a ramp, then the moment is something else. If it's a square wave, the moment is something else. So if you want, again, more details, I can forward you more details on that. But that is why this is the first moment differentiation, right? So first moment differentiation, what do I mean by that? You take the phi of x, you differentiate it once with the omega. Where is the phi of x? This is the phi of x. You differentiate that with omega once. Okay. And then, of course, whatever value is there, you find that out. And then you're applying that to find the variance. So you do that again. So see the variance, this is x squared. That's why you have to differentiate this twice. Now, differentiating it twice, what does it mean though, right? So differentiating twice, but with respect to 0. Omega should be equal to 0 wherever. So if you differentiate this equation twice, whatever comes out, you just substitute that with the value of a equals minus b. Now, why a equals minus b? Well, you're doing this first of all twice, and you're doing it at omega equals 0. So there comes, like if you differentiate that, you'll understand it better. Um, but yeah, so you're finding another variable and then whatever. So you just basically differentiate this equation twice. That's all. And whatever value comes out here, that's the value. Now, the variance is still not over. So the variance formula is e of x squared minus e of x whole squared. So you basically take 0, square it, it's still 0. And you basically take this guy, b squared divided by 3. Yep, so that's the answer. So that kind of this is the more important parts of the exams, okay? So just to repeat from the very beginning, before we move on to the testing methods, you need to actually want to learn how to find out the value of C, and from there find the CDF, sometimes plot the CDF, find the value of the mean and the variance from this. Now, finding the mean and the variance from this way and finding the mean and the variance from the transform way, if nothing is mentioned, let me see. If nothing is mentioned, then actually just use the more simplistic way of finding, which is from here, right? Uh, and by from here, I mean from the normal procedure that we follow in step A, step B, step C, and step D, right? So E of x is basically use the formula x fx dx. That's what I mean. And if they tell you to find it by this way, that from by applying moment theorem, then only apply the moment theorem. Otherwise, you do not need to apply. Oops. Otherwise, you do not need to apply the moment theorem. Okay. Now, other than that, you have functions of one random variable. Again, the starting part is very difficult, so please note this part, right? Sometimes we forget how to start the problem. And then you also have problems like if you have function of one random variable, find the CDF and the PDF. Simple processes. Again, find the mean and the variance of x if there is a 3x plus 2 kind of a function. So same thing. This and this, there's not much difference. Just remember that variance is not standard deviation. That's all. And then, of course, you have Gaussian problem. Gaussian is not very relevant, but still we need to actually learn it. And then we have the first problem that we actually solved, which is basically your finding the C. So now, oops, that's not what I want. But I'm going to actually anyway go through this lifetime kind of a problem. Lifetime problems are not really important. There are various ways of doing lifetime problems, okay? Reliability or lifetime is important for people who are working in embedded systems. And not only embedded systems, we can actually properly calculate the lifetime of a transformer or breaker circuits or any other things as well. That's not the point. Or even you can actually calculate the lifetime or the complexities of an algorithm. For those of you who are going to be machine learning engineers in the future, you can basically calculate the lifetimes of anything. Now, for here, this is like hardcore failure detection. Okay, so failure detection again in circuit parts in a whole module, it depends. Okay, but again, there are advanced ways or advanced softwares right now, but it's kind of based on the same principles. That's why it's important for us to kind of learn the essence of what this reliability is, what MTTF is, and why are we calculating the failure rate. So First of all, if you get a complicated function, always try to plot the function and look like what it is to you and what you're dealing with. Okay. If you do look at it properly by plotting it, you would find a lot of ease of working. Okay. So, for example, the reliability formula, first of all, let's give out the formulas because, you're going to make the cheat sheet anyway. So basic reliability. So these are all basic reliability calculations. Again, there are this itself is like a big course, like reliability and calculations and teaching how hypothesis testing work and all the test cases. So this itself is a whole different like subject in itself, okay? That can actually be taught. So that's why these are like basic calculations. So the failure rate is given by RT is equals P of t greater than small t. So there is a threshold that you need to pass. That is why after you pass the threshold, the object of whatever you're testing becomes desirable. Now, you cannot predict how long it's going to work unless you have enough number of data that, okay, even if it is faulty, it's going to work for 6 months or 8 months or 1 year, something like that. So anyway, so that is why it's greater than that capital T, that is the random variable, should be greater than a specific threshold for it to be reliable. So obviously, if it's greater than, we'll change it to 1 minus less than. That's a basic math. And then we have a couple of logics where we come finally to the MTTF. So the MTTF is basically the expected value of that specific variable T, and T is basically going to be a negative increment. So R of T dash that we say is negative of FT of small t. So the PDF that you have, you are going to take the negative PDF. Now, it's very difficult, okay? Now, let's actually go back to, and I'll tell you why. Remember, fx of x is always greater than 0, right? So when I first taught this course, I was like, uh-oh, how am I supposed to explain that to students? Reliability is always, so this is reliability, okay? This is not your PDF is obviously positive, but we are deliberately taking the negative of that PDF because of calculation purposes. So what you need to do, however, is MTTF. To find out MTTF is basically first find out the oops first find out the failure rate function, and then basically just integrate that function from 0 to infinity. Okay. Now, after you do that, that's exactly what they have done. They have found out the failure somehow, like in the scribbles that you have. Somehow they have found out the reliability of just substituting capital T greater than small t. And how do you reach from a small ft of t to capital RT of t? Well, you integrate, because this is kind of like CDF stuff. This is PDF stuff. They are not going to match with each other. Okay. So you integrate this specific function, you get the R of t. Once you get the R of t, you're going to go ahead and calculate your MTTF, which is basically, well, I mean, it's as straightforward as the formula. Like, it's just integration. So, I mean, I don't know how to further explain this. Like, now, there is, however, a part where there are sometimes asked about how many hours of operation can we do to achieve a certain reliability. So then if the reliability is given as 99%, then you back calculate it to find out what is or how many number of hours that we have to basically put in. And by number of hours, I mean we are trying to find out the T out here. By T, I mean small t. That is the threshold kind of value. All right. So this is your reliability calculation. Apart from this, I mean, this is not going to be too much of important for your exam, but I would actually highly recommend students to understand characteristic function, to actually go through problems on how to find out the value of C, how to basically substitute that value, find out CDF, find out PDF. Functions might be a little bit tricky, but what you need to actually keep in mind is the process. Once you master the process, the functions will not be of much significant problem, you know. So I would highly recommend people to go through problems like this guy. Whoops, no, that's not true. Yeah, to go through problems of this sort, right? Y equals e raised to x. How to solve that problem, right? And if you have learned how to solve these kinds of problems, by the way, then you can determine other types, okay? So there is going to be a little bit of twister, okay? I'm not going to lie about it, but the basic concepts are going to be the same, okay? So if you find a twister, do not sit and sulk on it. Move on to the next problems and try to solve them, come back again, and then solve any other surprise if you have in the exam, okay? The exam should be very straightforward. Again, 3 questions, a couple of parts to those questions, vary within the time problem. I need to, however, tell you guys that I won't be able to give you any extra time because I am very time bound that specific day. So please do not want any extra time for me. If you do, then I have to accommodate you in a very different location and I won't be able to do that. So keep within your time. If the time is up, I need to actually gather the papers out. So please cooperate with me for exam 2. Exam 1, I have given you half an hour extra, but exam 2, I'm very time bound that specific day. So I have to kind of finish the paper by 4:50 so that by 5 I leave the exam center. Okay. So please, guys, again, exam is easy, just 3 questions, but difficult from the sense that you need to revise your concepts. And I've given you a little bit of hints on how to revise. I hope you do really well. With that, I'll end the sessions. If you have any questions, please shoot. Oops. Oh. All right, guys, take care.